Hey, it's me, Destin. Welcome back to Smarter Every Day. We're on the way to my dad's work, and everything about this is weird. I have been trying to interview my own father for 2 years now at his work. The reason it's so difficult is because he has a really unique job. It's 2 a.m. Let's go see what he does. I think you'll understand. I cannot find the building because it's unmarked. I found his car just after driving around for a really long time. Okay, for a bit of context, my dad worked for the auto industry when I was growing up, and he's something called a metrologist. So as the parts came off the assembly line, he would make new, interesting ways to measure those parts. So right now, we are here at my dad's work. You can see there's testing in progress. Hey, is Daryl Sandlin here? How's it going?
Good. Say again, you need another stand for what?
Doing all right?
Very well.
Is my dad here?
He's in there.
Okay.
Is he?
Well,
In this room?
I said your dad is actually the one on the computer.
A beam in the way, but
That's him? Okay.
So that's my dad, and that's the bottom layer of the Sunshield of the James Webb Space Telescope. Hey, it's me, Destin. Welcome back to present tense, Smarter Every Day. So here's the deal. My dad did amazing things, and I got to investigate the James Webb Space Telescope in a couple of really interesting ways. First of all, I got to speak to Dr. Mather. He was the chief scientist over the whole project. I did a really interesting interview with him. It was fantastic. Feel free to check that out if you're interested in that. But also, I got to speak to my dad, who at this point in the video was working on the Sunshield, and he had been doing so for many, many years. So the Sunshield for the James Webb Space Telescope protects the optics of the telescope from heat and light from the sun and reflected heat and light from the Earth and the moon. It also protects the optics from all the electronics that are on the bottom side of the telescope. This is a critical part of the mission because in order to get the images they want in the infrared wavelengths that they're looking at, they have to keep the optics at a very cold temperature, and the Sunshield is what makes all that possible. There are 5 layers to the Sunshield, and they unfolded like origami 10 days after launch as the telescope was on its way to L2, which is the second Lagrangian point of the Earth-Sun system. So here's what I want to do. I want to go back in time to 2016 when I got to go into the clean room with my dad as he's working to measure the Sunshield for the James Webb Space Telescope. I'm excited to show you what he did because I didn't understand all of it, and I got to just ask questions, and for me, this is far more than a YouTube video. This transcends all the smarter. This is amazing for me because it's dad and it's me getting to ask him stuff. So let's go do it. Let's go back to 2016, get smarter every day with Daryl Sandlin as we learn about the Sunshield for the James Webb Space Telescope.
All right, so what's the deal?
This is the clean, dirty side of the room, that's the clean side of the room.
Okay.
Where you're sitting is the dividing line. So there he is.
We call this in French.
Well, I'm reading it.
So what's the veil for?
Breathing,
Yeah, spit and facial hair.
Spit.
Yeah, boogers, that kind of thing.
This is a hood.
this is the hood.
Is that right? Is that?
Yep.
Sharp. The goal is not touch the ground with it.
Yep. Right. And step over here. This is the clean side. There you
You're on the magical clean side now.
Yeah.
Well, it gets a lot harder once you're in here, doesn't it?
And we have all done this probably 5 times a day for the last long time.
Oh, yeah.
Are you serious? 5 times a day for how long have you done this?
It's been a long time, right? What, 4 years, 5 years?
Oh, more than that for the program. It's positive pressure from there to here for the attic room.
So all dust is blowing that way.
Right.
Gotcha. All right, so this is the core measurement group, right, Dad?
Yeah.
Or, yeah, measurement group.
So this is Bobby Thorne, and y'all worked together for 100 years?
25 at least.
It's combining almost.
I've known him for 25. I haven't seen him work for 25.
and this is Mark. And Mark, you're the specialist on the shield itself, right?
I say I'm a putz is what I do.
Okay.
I like to putz with everything. I've done process, I've done measurements, I've done a whole bunch of different things on this program. Got a patent on one of the things that we've done, so that's kind of nice.
Sweet. Cool. All right. My name is actually on the clean room access list.
Is it?
There's a D. Sandlin here.
Oh yeah, that's you.
I don't think it works that way, does it?
So it was kind of a big moment for me to walk in and be standing in the same room with this thing and my dad. It was one of those moments that you know will be special for the rest of your life.
This is my dad, and he's about to finish this major job you've been working on, which is the James Webb Space Telescope.
Sunshield for the James Webb Space Telescope.
Okay, so just so you understand, it's harder to get in this room for me than it was to go see the President of the United States, to talk to my own dad. You don't have any idea how much email I had to do to get in here,
I
do you?
have no idea.
It's ridiculous. All right, so what I want to do, if you don't mind, is, you know when I was a kid and you would teach me stuff?
Yep.
I'm going to do that only like 20 years later, and I have an engineering degree, and you've worked on the most expensive telescope to ever exist.
Yep.
Can we do that?
Sure.
Okay, let's go have fun. All right.
All right.
So this is what keeps the Sunshield.
What keeps the telescope shielded from the sunlight, earth light, moonlight.
Got it. Okay, and so that's because the instrument has to be really cold, right?
Yes, it does. Very cold.
All right, so this is like a potato chip sack or something?
Well, it's only 1/1000th of an inch thick. What you're seeing is 2/1000. This is the thickest layer. This is 2/1000 thick.
There's 5 layers, I understand.
5 different layers, right? And this is the flattest layer. And this is not the true shape of it. It's just on a 1x load. It's not the true shape of it right now. It's not under tension.
Gotcha. How does this thing hang up next to the spaceship?
That's the rim area. That's where the telescope will be. When we say rim, that's where the Sunshield attaches to the space telescope. We're in a structure right here that we call the verification structure. And
You mean these yellow things are the verification structure?
yes, yes.
So they simulate what? The cables that are pulling the tension on the heat shield?
We mount these pulley blocks. You see the pulley block here? Very precisely. We try to get them within 5/1000ths of an inch. But when we put different weights on them, these structures will flex or bend a little bit, will be loaded, and they'll move a little bit. So we try to put them in a position so that when we put them under load, they move into the position that they'll see in space.
So what you're doing, you're a metrologist, right? You measure stuff.
I measure stuff, that's true.
That you drug me all over North Alabama when we were growing up measuring stuff.
Measuring car parts. Yeah.
How the heck did you get to this from car parts?
Well, when I retired from working in the auto industry, I went to work for some companies that work for the Air Force, the Navy, the Army, medical things. I've measured things. I've measured knee joints, hip joints. I've measured a bunch of things. But nothing this big. This is really big.
Okay, so can we go over to the backside and look at underneath it? So I saw you measuring it the other day. They let me watch through that window,
Yeah.
and I saw that you guys had 2 types of measurement devices.
Yes.
Okay, you had I know a little bit about laser scanning. You had a laser scanner that would just do a 3D point cloud.
Yes.
And then you had point scanners, and you were using corner reflectors, right? Like
Yeah.
these little spots on the ground?
Yeah. Monuments in the floor. Yes.
So you're measuring the 3D shape of the Sunshield in relation to the floor?
Right. Well, the floor gets us a rough position on the verification structure. The floor is just a reference. There's a lot of different coordinate systems involved here, a lot of different coordinate frames.
Okay.
And the floor just gives us an idea of where we need to put everything so we can set it up relative to each other.
Really?
Yeah.
Okay, so what is the master coordinate system for the James Webb then?
It's the J1, J2, J3 system. It comes from that rim. Actually, the master coordinate system is down in the floor. And this is J2. J1 is forward and aft.
Are you talking about a plane or an axis?
Just an axis.
Okay. So this is the bottom side of the space telescope here. So the telescope's on the top.
This is the sunny side. This is what the sun will see. It'll be purple like this. This is silicon on this side.
So why would you have a dark color here? I thought you want a light color to reflect the sun's heat, radiation specifically.
I'm not sure. I measure the thing. I don't know. I don't know the emissions, the reflectivity. You'd have to talk to Mark or someone, an engineer for that.
Okay, gotcha. Okay, so one thing I'm noticing here is there's a lot of holes all in the space.
Yeah, it's holy, isn't it?
Oh, check it out. You can see our reflection in it.
Oh yeah, you can, can't you? Better on the other side on the vapor deposited aluminum.
Really?
Yeah.
So why are there holes in a heat shield? If you're trying to block the sun, why would you need a hole right in the middle of that thing like that?
Well, it's going to be folded up in the rocket that puts it up there, the Ariane's 5, I believe.
Ariane 5, the French rocket?
Yes. It's going to be folded up and stowed away, and when it launches, the air that's trapped in the Sunshield has to get out some way. So these are vent holes, air vent holes.
But won't the sun make it through that and hit the telescope?
Well, hopefully the vent holes that's in layer 2 will not be in line with the one that's in layer 1. And the vent hose that's in layer 3 is still out of line, and 4 and 5.
So these holes are specifically for deployment and nothing else.
Right, that's right.
So if they do their job, after that point it's just wasted space. Or it's a wasted feature. Okay.
Once it gets in space, you know, there'll be no air to vent, so this, you know the way the atmospheric balloons swell up when they, well, this is to keep that from happening to our nice sun shield.
Oh, so you're saying when it's folded up like a shirt inside the Ariane 5, the French rocket, as it flies up in the atmosphere, that gas starts to expand.
Yes.
And once it expands, it tries to blow the whole thing up like a balloon.
That's my understanding of it, yes. And
Okay.
that's what the vent holes are for.
Let's talk about scanning.
All right. Let me get a laser scanner.
Okay. How many years have you been doing this?
Laser scanner, the reason I took this job is because they got this device right here, and I had never used a 3D laser scanner before.
Uh-huh.
This is a Faro Focus 3D scanner.
You're used to using like XYZ coordinate measure machines, right?
Yes, CMMs, coordinate measuring machines. But this is, see this mirror, the way it turns right here?
Yeah.
I have a mirror that turns.
Uh-huh.
We mount it on a tripod or a high pod that we have over there. This mirror turns at a high rate. A laser comes out of here, bounces off this mirror. Now that laser is not very eye friendly. You have to be 35 feet away
Okay.
from it. Okay? When the laser hits this, it will make a plane, just a big plane like this at a very high rate of speed. It will take 975,000 points per second, XYZ points, and then this will begin to rotate like this. As it rotates, it'll take plane.
Oh, so
Paints the entire room.
so right now, if I were to cut a section right here,
Yes.
it would take a plane and then you would rotate it over like this. But
Yes.
this would be a pretty bad spot to do that from, right?
You can't see much from here.
So where do you do it?
Well, we do it in 7 or 8 different places. But what's important is these spheres. Can you see that sphere there?
Yes, I can.
This sphere over here. When we do the scanning from over here, you see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We want at least 3 spheres in view.
Can we go walk to a sphere?
Yeah, let's go look at the sphere.
All right, so this is the sphere.
Yep. About a 7-inch sphere.
What's important about that?
It's a reference point. When we do a scan from the middle, we want to be able to see at least 3 spheres in view. So that we do a scan, and then we take a laser tracker, and we precisely measure the position of each of these spheres.
Okay, so what you're doing is you're getting a hemisphere worth of data.
Yes. The scanner calculates the center of that sphere using one algorithm or one set of measurements. But the laser tracker will take 7 points on it using an SMR, a spherical mounted retroreflector.
A corner reflector.
Yeah, corner reflector.
Yeah,
You know about those.
I do.
And we get a precise location with it. The scanner is not that accurate, but the laser tracker is very, very accurate. So we measure these spheres, we compare where the scanner thinks the spheres are to where the laser trackers say the spheres actually are.
Okay, this gets a little bit complicated, so I want to jump in here and make sure that we understand the 2 different types of instruments we're using. The first one is a laser scanner, which pivots around the room and paints the area with a laser to give you a wide point cloud of what's going on. The second thing we're going to use is the laser tracker. The point of the laser tracker is to precisely measure individual points. We're not painting an entire area with the tracker, we're just locating one specific hard point to a high degree of accuracy. Okay, so two tools. Laser scanner paints a wide area, gets a point cloud. Laser tracker gets us individual points to a high degree of precision. This episode of Smarter Every Day is sponsored by KiwiCo. KiwiCo is a really cool company that loves inspiring the next generation of learners. KiwiCo has come up with this really cool way to engage young minds by sending crates to your house that are themed along a specific line. There's 9 different lines to choose from. You can get the panda crate, koala crate, a tinker crate, doodle crate, it goes on. They come to your house and you open the box up and there's all kinds of stuff in the box. Everything you need to build the whole little kit is right there in the box. What are you working on?
I'm working on a crawling robot.
A crawling robot? Looks like a crab, doesn't it?
Yes.
You think it's gonna work?
Yeah.
What are you working on, little girl? Oh, you're exploring stars. How
But
appropriate.
that's the one I'm about to do. But that's the one I'm gonna do.
Oh, so there's like 2 kits in one?
Yep,
Oh, cool. You get 2 projects. That's awesome. You excited?
sure am.
There's also step-by-step instructions that tell you everything you need to do. It's amazing. We love KiwiCo, and we know your family will as well. If you want to try this out for you or a kid you love, go check it out at kiwico.com/smarter30. That gets you 30% off your first kit. I reached out to them to begin with because I knew you would love it, and I only like to work with sponsors that I believe in. I know you will enjoy KiwiCo.
Watch this. When you take it out,
Oh, look at
Alexa.
that.
and then it goes, I'm the sun, I'm the sun, I'm the sun, I'm the sun.
Can I test the eyeballs real quick? If you want to try KiwiCo, you can do it by going to kiwico.com/smarter30, and that gets you 30% off your first crate. Does that work, buddy? I can't see you. Am I pointing the camera at you? There you go. Sorry. A big thanks to KiwiCo for sponsoring, and a thanks to you for considering supporting the sponsor, which ultimately supports Smarter Every Day. I'm grateful. All right, so this is the tracker, right, Mark?
Yes, this laser tracker. We've got floor monuments. We've got holes drilled in the floor for solid points. What they'll do is determine a frame of reference relative to the structure and the rim, the pulley block points, which allows us to take tracker measurements from different spots. So what we've already done is we bucked into the floor. We've measured 4 monuments. Now we have a frame of reference. The frame is actually about a foot underneath the floor right now.
So basically, the tracker knows where it's at.
Yes, it's called locating the instrument.
So we've located the instrument.
Where it is compared to everything else. It does all of the transformations, and that way we can point at things. It makes life a lot more convenient. We've got a measurement script that says go here, go there, go there. So when Bobby and Daryl are running around in the middle of the night making measurements, I'll call out where we're measuring. They'll make measurements, and
Can we simulate a measurement now?
yes.
All right.
For instance, we've got, I'll point it to that sphere over there. That is sphere number 3. We got 1, 2, 3. We just go clockwise around the membrane. 7 and 8 are in the rim. So I'll point at that one. We'll do a simulated measurement for S3.
Okay, sounds good.
I'll do point to S3, and you'll see the tracker swing around. We got a dot in the center of that sphere now.
So this is your retro reflector. This is a corner reflector.
This is a corner reflector.
And I can tell that because anywhere I move the camera, I can see the camera lens in the corner reflector.
Right.
All right, cool. So how do you locate that sphere?
Well, the tracker knows where the center's supposed to be. We'll take this and we'll measure up to 7 points around it to get the actual position of it.
Okay. So you just bump the side of that sphere up next to that sphere.
I touch it, but he'll point to it and he'll say, I'll acquire the beam, which is what I'll do right now. The laser tracker will turn green when I do this.
All right.
When I intercept the beam. So I will intercept the beam now. All right, I have the beam.
Okay, so I can see it in the corner reflector now. So you can carry the beam with you.
Yes, now I can touch the side of it, and it knows that I'm touching it. I'll move it a little bit, and then the software will say, waiting for stable, waiting for measurement. It will wait until it gets quite a few measurements that are stable, not moving, and it'll acquire 1 point. Then I'll move it When it stabilizes, it will acquire second point. I do this 7 times. 4, 5, 6, 7. What I try to do is go to the North Pole, go around, describe a hemisphere, and then take an equator so they get a good hemisphere. It takes those 7 points and calculates the exact center of the sphere.
But if you had all of the points around the perimeter of it, you wouldn't be able to get depth in as high of a tolerance.
Right, it's a 3-dimensional surface, you know. It's a 6.9 inch sphere. All of them are about the same size.
So it's important to define as wide of a position as possible.
Not just a circle, not a plane, but the 3-dimensional center of the sphere.
Got it.
That's what the laser scanner, this center, all these spheres here from each point will be compared to the scan. And that lets us position the scan relative to.
So it's a temporary datum.
Right. But it's the most important, the most accurate datum that there is.
Because it never moves.
So we've got labels on all the points we measure. As you can see, we've got a sphere right here. It shows the sphere center. And again, the data says that it was within less than 3 mils of position.
3 mils meaning
3 thousandths of an inch.
0.003.
0.003 inches.
Got it. That's pretty tight.
Yeah.
That's pretty tight when you're talking about measuring a big plastic surface like this.
And I'm sure Daryl already explained to you that these are the registration spheres for the scanner. The scanner does not actually register to the coordinate frame. This is our reference for the scanner to get back to the coordinate frame for the rest of the system.
It's a temporary datum. A laser scanner works by shooting some photons from one emitter out to something and then getting a reflection back to a detector. And if I know how long it took in time for that light to go out and back, and I know the speed of light in air, then I can just use algebra and I can figure out how far away the object is. That's pretty cool. The second thing is if I know where I'm pointing my laser at the time in both azimuth, left and right, and elevation, up and down, then I can use trigonometry to calculate a 3D coordinate of where that thing is. X, Y, and Z. Boom, that's your 3D point. You get a point with a 3D coordinate, and you do that a cajillion times, you can define a surface or the shape of something. Here I have some metal, right? Kind of reflective. If I'm going to scan this thing, the ideal way to do it is to get my laser scanner as orthogonal to the object as possible, meaning I want to hit it straight on, 90 degrees, right? Because I'm going to get a bounce back laser return and I can measure that, right? But if I measure a reflective object at a shallow angle like this, what will happen is my light beam will go down and it'll bounce off the shiny object. For that reason, Dad and the team always tried to position the laser scanner in the most orthogonal spot possible, meaning as close to 90 degrees as they could get. The problem is, because this thing is so big and the room is like kind of confined, you can only position this thing in certain areas. So you might be able to get a really good shot on a close-up position, but not far away. It's pretty interesting to think about, and the team has a lot of really interesting tricks to deal with this.
These are laser targets.
Those white, are they paper?
No, they're not paper. You can't have paper in this room.
Okay.
Because of particles. But this is flash breaker tape. They are targets too. They're very precisely located with a laser tracker so that you can look at the position of these and you can calculate the light.
Oh, I think I just got it.
Yeah.
I think I just understand. There's two types of reflection of light, right?
Yeah.
There's specular and diffuse.
Yes.
Right?
Yes.
This is specular reflection. This shiny surface is a specular reflective surface, right?
Yes.
The diffuse is what I'm seeing on those targets.
Yes.
So is it true that the laser scanner can pick up the diffuse reflection?
Much better than the highly reflective stuff. So you can tell where the surface is.
But there's no way you're going to fly that diffuse.
No, they're just laying on there temporarily. They have very low mass. They're not reflecting the surface. They will actually move. I don't want to touch it right now.
Right.
But they'll take these off. This is tape. They'll take this tape off. And what you'll see is just the shiny part there.
Gotcha.
I'm going to turn on the surfaces, and then we're going to colorize the surfaces. Render those.
Oh, so it knows what the shield is supposed to look like.
Yeah, we have a predict model for the shield in here. I'll go to top view. So that's what it looks like. We can turn any of these features on and off. Again, we have them labeled. And I can point to any of these features in here at this point.
That's pretty cool. So the final data product here, who processes the data? Is that Naveen's job?
Naveen will process the data. We are the measurement monkeys.
And what is the final data product?
The data product, yeah, you can see this one's only 6 mils off.
Yeah.
That's how tight we set the pulley blocks up, and that's where it's. The data product is a plot of the shape of the membrane in its coordinate frame, and we have to tell it how much this membrane shape is RMS. So all these hard point measurements are support functions for the scan measurements.
Gotcha.
I want to take a second to talk about what the team is doing exactly. Number one, they have a laser scanner that's measuring point clouds, and they have a laser tracker that's measuring precise points. The team has to measure this really big sunshield, and the sunshield is designed to block light, which is what these instruments use. So they can't set up in one position and measure everything because part of it might be shaded by another part of the sunshield. So they have to position these instruments all over the room and then add up all that data into one data set. To do this, they position spheres in the room, and these spheres don't move over the entire measurement process. Every time they set up an instrument, they have to be able to see at least 3 of these spheres because the centers of any 3 of these spheres define an exact 3D plane between those 3 points, which could anchor everything back to the external coordinate system. So if they could see more than 3 spheres, that would make their measurements even more anchored, so they always try to locate as many of these spheres as they can so that they get more accurate data. For example, the data from one scan may look like this, and the data from another scanning location might look like this. By doing a coordinate transformation and aligning every scan up with the reference frame defined by these 7 spheres, they're able to create a common coordinate system that can be used to simply add up all the scanning data and create an overall measurement of the shield. Because each scanning setup can only see a portion of the sun shield, the spheres are the key to tying all the data together. They move around the room, repositioning the instruments over several weeks to get different vantage points of the sun shield, and then they add all this data up to create a 3D model of the entire sunshield as it exists physically, accurate up to 5/1000ths of an inch. To get all of the sunshield geometry, top and bottom, tip to tail, the team usually had to set up and measure from at least 9 different instrument locations to get all the data. This process seems straightforward enough for one sunshield, but when you realize this routine was performed for every prototype, every repair or modification, and the final flight hardware for all 5 layers, that's why my dad worked on this project for so many years.
Tell me this. If you've got the surface here,
Yes.
I mean is it Mylar?
No, it's Kapton.
Okay.
Kapton.
So the material that makes up the heat shield here is experiencing weight. It has weight here
now.
because we have 1G pulling it down.
Right.
So you're measuring it in a 1G environment. How do you equate that to a weightless environment?
Smarter people than me figure that out.
Oh, really?
Yes, they do.
But that's what they do. So like Naveen, he'll take the data that you give him,
Yes.
and then he has a way of turning that into a weightless type measurement.
Yes, he'll compare it to the finite element analysis of it, and we have people that do that, and we'll put it under a 3x load, and what you're seeing right now is a 1x load. All we're doing is just holding it up off the floor, really. We're just supporting it right now.
Okay.
This is not the final shape that you see. When we did the test a couple of nights ago, that was...
The one where I was watching through that window over there?
Right.
Everything was really tight then.
Yes, it was.
Okay, so it's a more stressful test.
Yes, it is.
Okay, gotcha.
Once Bobby, Mark, and Dad get all this data, they have to hand it off to an analyst who's really good at math so they can do all these coordinate transformations and add all their scans up so they can compare it to a model, is my assumption. Now, the reason I usually hear of engineers comparing things to models is you want to see what spots are high and what spots are low and see what's messed up. But the good thing is I actually know the guy that did the analysis for him. His name is Naveen, and he's a buddy. So let's just call Naveen and go ask him what he did. Okay, fast forward to now. We're like 6 years ahead from the timeline of the video here. Not only is Naveen super smart, you're PhD in like fusion or something like
Nuclear fusion.
Nuclear fusion, okay. But we're buddies. Yeah. We've known each other for a while, and Naveen worked with my dad, true?
Yes,
but
on James Webb.
Real quick, like you actually love
Astronomy.
space.
Yeah, anything space.
Anything space.
Especially astronomy.
Okay, so I wanted to interview Naveen up here because this is VBAS, the Von Braun Astronomical Society, and you're on the board, right?
Yeah, I'm an officer and I'm mainly the outreach coordinator. So we take telescopes to schools and museums and look through the telescopes, the planets, deep sky objects, and all that.
So James Webb was more than a job for you. It was like a passion, right?
Yeah, it is. It was, and it still is actually.
So Naveen was the smart guy that Dad and the team would take the data to. When they would measure with lasers, they would get a huge amount of data and they would bring it and they would drop it in your lap.
Yep.
And my question is, why? What did you do with the data?
So there is this data is LiDAR data, so it's kind of light detection and ranging. So it's a lot of points.
So you're really good with MATLAB.
MATLAB, any programming software, but this one is mainly coordinate transformation. It's called photogrammetry. You see that in when you are taking topographical pictures of different landscapes. So we did something similar using the scans, and you have, depending on where you put the scanner, so it will give you different point cloud.
Right.
So now we need to do the appropriate coordinate transformation to make sure all the clouds align, and then we clean that data to compare it with the finite element model.
So step one, you've got the spheres throughout the room. Mm-hmm. So you would use those spheres as anchor points.
Yes.
And then you would take whatever the scanner saw there and you would transform it.
Yeah, exactly.
And then you would line up all the data.
All the data.
Okay, but after that, after you added all the data together, you had the true point cloud of the entire Sunshield.
Yeah, that's used to be like 10 gigabytes of data or something like that.
Of just XYZ points.
Yeah, just points everywhere.
Okay, and so Dad told me a couple of interesting things. He said that when you guys were measuring the Kapton, it's like a big kite. And he said when they were actually scanning, they had to sneak through the room because of air movement. Is that true?
That's true. Yeah. We had to shut down all the air conditioning, HEPA filters and all that, and then walk very, very slowly.
Yeah.
Luckily, we did all the testing in the middle of the night, so there isn't much disturbance from outside. And whenever we used to go, only 1 or 2 persons used to go into the clean room and walk very, very slowly to change the scanner location.
Like you assumed a position,
like that. Sometimes just like that.
Really?
Yeah. So when a helicopter flew over the building, the vibrations due to that helicopter flying over the building could actually be felt on the Kapton layer, and we could see it. So what we used to do, we used to write down, okay, at this time in the night, helicopter flew over the building. In that way, when I get the data, I look at the point cloud, I could see that sometimes.
Really?
Yeah, in that region, you could concentrate it and you can see some kind of ripple kind of effects.
That's insane because it's the vibration, because you were measuring that accurately.
Yeah, laser scanners are very, very accurate.
Oh, okay, so this is the question. I get it. You're actually defining the shape of the actual Sunshield as it was fabricated.
As it was deployed under Earth's gravity.
In Earth's gravity.
In Earth's gravity.
So my question is, it's in space. So how do you compare a 1G environment to the 0G
That's
of
a
space?
pretty good question. That's the reason why we deployed in the Earth's gravity to measure it, and we compare what we measured with a model, finite element analysis model.
Okay.
And in the finite element analysis model, we predict how the shape looks like in Earth's gravity. And we compare the test data with the model data, and then we can see how good the model is. If the model has it differs by certain amount, which is acceptable, then we can immediately use the model to predict the shape in zero gravity. Because we have confidence in the model. So
it wasn't so much about measuring the actual shape, it was about developing a model which could be used while it's in space.
Yes.
Okay, and why does it matter? Like why does the shape of the Sunshield out in the middle of the Sunshield matter? Because it sounds like if you're just trying to cast a shadow, like if you're the instrument, as long as I'm blocking you, what does it matter what the Kapton is doing out in the middle?
It's not only blocking the light, it's also about the heat. One, heat is coming from sun and earth. Heat is also coming from the telescope bus where all the instruments are. They are generating heat. Yeah, underneath that box is creating heat, generating heat. We want to make sure this heat is all radiated outwards.
Okay.
And that shape, the gap between these 2 layers or those 5 layers plays a very, very important role in dissipating or it's radiating that heat out.
So it's just reflecting it off.
Reflecting outwards like that, and it's like reflects, goes up, reflects down, reflects up, reflects, goes down. and then it goes out like that.
Oh, is this like a pipe? So you're like, it's bouncing back and forth till it goes out to the side?
It's just like a light, right? Light bouncing off two reflective material, between two reflective materials. So you have...
Shut up. You have total internal reflection of heat?
Yeah, yeah.
And you're like dissipating it out to the sides?
Yep.
That's why there's 5 layers?
Yes, exactly.
Okay.
It's all radiating the heat outwards.
Okay, I had no idea. So it's not about a shape model. I mean, that's part of it, but it's about a heat model.
But the shape is what is directing the heat out, right? So the shape is important.
Explain.
If we have only 2 layers that are like flat,
Okay.
well, how is the light going to, or the light or the heat that light is bringing in going to go outside?
It's just going to bounce back and forth like this.
Yeah.
Okay.
But if you play with the shape, I don't want to go into the details, but if you play with the shape and you have the right shape, you can direct this heat that is generated at the core, at the bus, the bottom box, you can direct it in such a way that it just radiates out.
So Dad was measuring points to predict the shape using a model. You were validating the model in 1G so that when it's in 0G, you could then use the model to determine if the radiation pipes or planes were working correctly.
Yeah.
I've known about this Sunshield for years, and I never knew that was the point. Did Dad know that?
I'm not sure.
He just measured it
Yeah.
went to lunch with you and gave you the data.
No, these technicians I wouldn't do these technicians' job. They are so precise. I don't have that kind of experience to be so precise. If they want to weld something, like for example, thermals, the seam bonding, they're so careful about that. Where in exactly the light line should stand on the entire Sunshield. These technicians were like really amazing. I wouldn't do that. I wouldn't even touch. I probably touched the layer maybe 10-15 times. That's it. Yeah. I wouldn't want to touch that.
That's amazing. Okay, I had no idea what you did, and now I do. Thank you very much. I appreciate it. So now we'll go back to the past, and we'll see how the team is finishing up with the data. Does that make any sense? You're in a video. You're in the middle of a video here.
Oh.
And we're going back in time now.
Okay. What? So, are we talking about time travel here?
Basically, yeah. Okay. Basically, that's what the James Webb does, kind of, right?
Okay. So yeah, it is going all the way to the beginning of the universe. Yeah.
So this is like this is an art, right? This isn't like just gluing together a potato chip bag. This is
no.
that's where the secret sauce is, right?
It's precision. It's precision. And you have to be, or you would, when you stretch it out tight, you would have folds and yeah, it has to be very precise.
Gotcha. Okay, so that curve right there, you've told me about this over dinner a couple of times. What is that curve?
It's called a catenary curve, Catenary.
Okay.
It's like the curve that a chain or a string would have if you suspended it from both ends.
Okay.
Fact check that just to be sure.
I will.
A catenary curve. So if you apply force here and down there, that's the natural force. It'll spread out to make the center of the Sunshield be tight like the head of a drum.
My dad gave a really good explanation of what's going on with catenary curves on the James Webb Space Telescope by using a model in the viewing room, but keep in mind that this model was several years old, so it's not up to date on the latest design that flew up in space. However, it gives you a pretty good idea of what's going on.
This force vector here, along this force vector, would define where this catenary curve is.
Okay, and so that's the curve that basically suspends the whole sheet.
You got one right here and one right here. It's kite shaped sort of. But the real force stretching this thing out, putting the tension on it, and really I'm not the person to ask this. I'm a measurement man. I'm a test measurement specialist.
Okay.
I'm not an engineer who stretched this drum.
Okay.
But look up, for your smarter every day, look up catenary curve.
Okay.
You know what one is. If you hold a string up like this right here from 2 points, that curve that a chain will follow.
You know why I know about it, right? Because you taught me about it.
Okay.
You were teaching me about hyperbolic sine functions in high school, and I didn't want to learn about it.
Yes.
That's why I know about it.
Yes.
Yeah.
Well,
so if I'm not mistaken, I always put an N in there for some reason. A catenary curve is a hyperbolic sine function. I'm told. I might be wrong.
Probably so. I don't know.
Okay.
I would check that before I said it out loud. I would check it.
Okay. So
The light lines are straight lines right here. The pulley blocks that you see out there have 3 pulleys on them. You have a hold here to here.
and that defines this curve,
That defines this line right here.
the light line, okay?
Light line. But this curve is defined, and I'm not the one by the tension on the main pull here, and the tension on the main pull here,
Okay.
and there. So these 2 curves are terminating this grommet.
Got it. What's this table over here?
This is an assembly table when we need to inspect or attach or lay out the things that are attached to the membrane. They put it on this table here. The gantry is designed so that you can go over it and you can work on it without.
Oh, so you float, you lay on your belly here.
You lay on your belly, yeah. We actually have a board that you can see back there that you can push around portable, but you can only reach about 10 feet inboard with the belly boards.
Gotcha. So you lay on your belly on this thing,
Yes.
and then
6 of us can lay on our belly.
and then this rolls out like a crop irrigation system.
It does, exactly.
And then you can get to different spots on the shield.
Right.
Huh.
And the laser tracker over there in the corner,
Yep.
pinpoint a precise point, target it, we can mark it, and the technician can come by and either punch a hole or adhere a part to it.
Oh, that's
Whatever the technicians do, you know, they do a lot.
really. How do you position the holes on a print?
Yes.
So this is I'm looking at a curved structure here.
Yes.
So in order to create a curved structure using a planar tool,
Yes.
how the heck do you do that?
Well, Pro E, which is a design software that I'm sure you know a lot about, can flatten it and can do it. Northrop Grumman gives us the position or the recipe or where these holes go, and we put them there. We mark where the punches go with the laser tracker, and then we come through, we get them within 30 thousandths, and then we come through again and we fine tune them to plus or minus 3 thousandths of where the hole is supposed to be. And then the technicians come in and they punch these holes, and then we go through and we measure it again to see if the punches move during the production process.
I mean, with a big sheet of material like this, what are you going to do if a punch is in the wrong spot?
We don't want that to happen. We take many safeguards and double checks to make sure.
Measure twice, cut once kind of thing?
Yeah, absolutely. And you got other people looking at what you do, but you can patch it if you make a bad mistake. Don't think we have any patches that I'm aware of, but it could be done.
Huh.
You know.
Huh. That's interesting. Is it okay if I go to the center?
Yeah.
I'll get Dad to go with me. So this is what the instrument's going to be positioned at.
The telescope will be right here in this ring.
Gotcha. And so all this Sunshield protects it
Right.
so you can keep the instrument on the correct temperature.
Right.
Man, look at that. That's pretty neat.
It is. Isn't it?
How long have you been working on this?
About 6 years. I came in late 2010, November 2010.
You've been making and measuring this thing with the team for 6 years.
Yes.
Have you been here for 6 years, Bobby?
No, I've been there but 2.
2?
2 years.
Oh, you just came for the final part, huh?
Well, I've been involved in all 5 layers.
Oh, really? So the layers weren't created until the last couple of years, or measured.
The final layer, the test layers and stuff like that.
Oh, so you guys made this before you actually made it?
Oh yeah, we measured everything on these things here.
Oh, wow.
But the manufacturing process had to be developed. You know, they made practice layers first, and then they measure them, see how close they were and everything. But the final flight material, which is what this is, was done in the last 2 years. Flight material that will actually see space.
What's it like to work on something that is going to be on the other side of the moon?
It's tiring. It's a lot of work.
Really?
Yeah, it is, Bobby.
I just want to see it fly.
You want to see it fly?
Yeah.
Man.
Bobby and I had to put all this structure in place in the right position and everything before they could hang it. Bobby had to do most of it. My back's been hurting the last 2 weeks. That man's been carrying a heavy load for the last 2 weeks.
Yeah?
I couldn't, that's right.
That's awesome. So he's been a little bit of a sissy man and you've had to help him?
He's cool as that.
Sissy man. Sissy man, yeah.
I said, this thing is put together like a big quilt.
Quilt, yeah.
Is it welded together, like you heat it together and?
Basically, yeah.
It's called thermal bonding. It's a process that the company that we work for patented it, and it's their
So it's a proprietary process.
No adhesion, yeah.
So this is the only place that happens.
We're the only ones that can do it.
And the company is called what?
Mantech Nexol.
Okay, so Mantech owns the process that creates this Sunshield.
That bonds the layers of the Sunshield.
That's the secret sauce.
The secret is, yeah.
Huh, that's interesting. That's why
it's in Huntsville.
Really?
That's why it's here, yes.
Because Alabama guys are doing it?
That's right.
That's funny. So Bobby, I noticed you put a corner reflector right here, and this is to simulate the telescope itself, right? This is the rim? Okay, so what really matters is where everything is in relation to this surface right here.
Yes. This surface is flat within 0.005 of an inch. Isn't it, Bobby?
Yes.
we work hard to make this surface right here, the interfacing surface, flat within 0.005 of an inch.
You have to shim it?
Oh, yeah. The shims you can see shims right here. See those shims here?
Yeah.
Torque on these bolts.
How long did it take you guys to get it that flat?
2.5 days, but we're good at it now.
That's the way it always works. Once you do it and you're done, then you're good at it.
That's right.
All right, we leaving?
Yeah, we're leaving.
Okay.
So Dad and Bobby slipped away, and I took a moment to get this panoramic view from the vantage point of the telescope, like right in the center of the Sunshield. This is the spot where the telescope is literally going to be making historic astronomical observations that'll give us a glimpse into the deepest reaches of time and space. And when I started to think about it, I realized this is a very significant moment in a very important spot, and I wanted to document it in a very special way.
Can we take a selfie together?
Yeah.
From the spot where the telescope's gonna be?
Yeah.
All right. Don't touch the flight hardware. All right. Look at the lens. 3, 2, 1. I think that'll be good for the Christmas card.
Yeah.
Are you ready to be done with this project?
I'm tired.
Well, I mean, you're
Yeah.
tired and old. I mean,
I've measured many things.
I mean, just this is 4 a.m. after an all-nighter running a laser scanner. Daryl Sandlin talking.
I'm tired, but yeah, this is the last layer. And before we did these 5 flight layers, we did 5 template layers, which was practicing and developing in the process. So this is 10 layers that we've done this size.
So this is
The last 6 years, this is what I've been doing.
So tonight's the night.
Tonight's the final layer 1 acceptance shape test. Now, a lot of people's got to look at this data and make sure we didn't do something wrong.
So what are they doing here?
They're going to build a cradle so that when we fold up the membrane, the layer, they're going to lay it in it, encapsulate it in clean poly, and later on they will purge it with nitrogen so that nothing can get to it. But they're making a...
So I need to get out of here and let these guys work.
We need to let them work, yeah.
Watching the team fold up the Sunshield to ship it out to California is amazing. It's a beautiful and complex origami dance of sorts, and to me that represents the whole James Webb Space Telescope program. It's an amazing technological collaboration of a bunch of different people working patiently together to accomplish something truly extraordinary.
Standing by for terminal count.
They better not burn up at Sunshield.
And we have engine start. And liftoff.
Boy, that thing jumped off the launch pad.
Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Oh shoot, that's what's happening right now.
What?
The rocket goes up, and those holes that you put in there that you spent half your life putting holes in that thing, that's to let the air out on ascent.
That's true.
That's what just happened.
From the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
I want it to work. It's going to change our thought process. It's going to change the way we think, just like the Hubble did. These mirrors were made in Cullman, Alabama. That's there, and the Sunshield was made in Huntsville.
Extraordinary things are done by ordinary people. This is my dad, and there's 10,000 stories just like his of people who worked on this telescope. When they started, this dream was literally impossible. Many of the technologies didn't even exist yet. But each team worked hard to overcome the problem in front of themselves, having faith that every other team would do the same. In the end, thousands of people from all over the world came together to make this thing a reality, and I think that's really, really beautiful.
I mean, never imagined. I grew up in India in a small town, and where there was no television or telephone. The first time I saw NASA was in my dictionary. I used to speak a language called Telugu. My dad brought a Telugu English dictionary. So every English word is translated into my language. So I saw NASA first time in that.
Yeah.
I never imagined I would even come to the United States and got to work on a telescope like this, which is now in space. So I'm excited about that.
I hope you enjoyed this video. Obviously, this is super special to me. I'm really proud of my dad. He's taught me so much through the years, and it's just, I don't know. This makes me feel things, and I hope you enjoyed it. One last thing, I'm not really a merch guy, but I really wanted a shirt for the James Webb Space Telescope, and I wanted it to have all the science on it. And so this one, I commissioned an artist. It's got the Earth, the Moon, it's got L2, 4 times the distance out there. It's got 5 Sunshield layers, and that's actually the orbit path around L2, so I took that from a research paper. I just wanted this for me, and I had it made, and so I think you might like it as well. If you want one of these, I'll leave a link down in the description. No big deal if not. I think it's awesome. That one has a rainbow on it. I think it's cool. Anyway, that's it. I'm Destin. You're getting smarter every day. Thank you so much. Also, thank you to the patrons. I'm grateful. Have a good one. Bye. All right, so what are we doing now?
Always good to go to the bathroom if you have to.
Yeah, you gotta go to the bathroom.
Go in.
I don't.
That's important. This is like a laxative when you get this stuff on.
It makes you have to go. All right, so what's the deal?
This is a clean, dirty side of the room. That's a clean side of the room.
Okay.